Okay, we're going to look at another part to the fundamental theorem of calculus. So to introduce this, suppose we're looking to find the derivative of this integral that we see. It's a definite integral. It has bounds from pi to x, and then we see cosine of t dt. Now, first of all, notice how these variables match, and then notice how these variables match. That's very important. You're always going to notice that relationship in these types of problems where we're looking to take the derivative of an integral. And we're going to see why in a moment. So if we were to work this all out, we would first start by doing what's on the inside here. So let's ignore our derivative notation for now, and let's just evaluate this definite integral. Well, we know that when we integrate cosine of t with respect to t, we're going to get the sine of t, and our bounds are from pi to x, and we know from there, oop, my coffee's beeping, it's ready. Alright, so from there we're going to drop in first x and then pi. Okay, and let's stop there and let's now come back to this and copy over our notation here. So d dx means the derivative with respect to x. And notice now that after we evaluated this expression up above, notice how the t's became x's because the x got substituted in here for t, right? So when we put our bounds in here of pi and x, the t was replaced with an x. So we're now looking to find the derivative of our answer. Well, again, notice how these are matching because, well, if we're going to find the derivative of this, all right, we would expect that to match. So our independent variable is x. So from here, the derivative of the sine of x will be the cosine of x. And then the sine of pi, this is just a constant. This is just some number. All right, and so the derivative of that is really 0, so we're technically subtracting 0. So we can conclude here that our final answer is just the cosine of x. Well, we could have gotten that a lot quicker if we were to go back to our original problem here. All right, if we go back to our original, your common sense is hopefully telling you that, okay, the derivative of an integral, those are going to cancel each other. Okay? And what you're left with is just what you have on the inside. All right, and we know this dt, by the way, goes with the integral symbol, so that would also kind of disappear if you're taking the derivative of an integral. But notice how our final answer was not the cosine of t, it was the cosine of x. So notice how this bound, this upper bound of x, all right, gets dropped in there. So notice how the upper bound is a variable and the lower bound is a constant, okay? So let's just make note of it. The upper bound here is a variable, and notice how this lower bound is a constant. So that's going to lead into what we call another part of the fundamental theorem of calculus. One is called part 1, the other one's called part 2. It doesn't matter which part number they are. They're both affiliated with what we call the fundamental theorem of calculus. So here it is. That's good coffee. Alright, so here's what I was talking about. Here's a summary of what we just looked at. So the derivative here of an integral, again, notice how these match up and how these match up. In the end, you're just going to have f of x in this case. So this variable, that upper bound of x, just gets dropped in there into the function. And recall that this lower bound is a constant. Alright, let's check out this example. We're trying to find dy dx, so the derivative here with respect to x. And we have this y equals equation, and notice how it has an integral in it. And this time, notice that the upper bound is x squared. It's not just a plain x. So what we're really looking to do here, this is the same as finding the derivative with respect to x of this integral from 1 to x squared. And then we see the sine of t dt. So from here, we said how these are going to cancel. and we're going to be left with this dropped in for our variable. So we're going to end up with the sine of x squared. But what we have to be careful about here is we need to remember to chain along the derivative of that upper bound. The derivative of that upper bound is 2x. Now, what is not going to cancel out is the chain rule part of your derivative. Okay, so let's make note of that. Okay, so there you go. I'm not going to show it here in this video, but I would encourage you to work through this the way we did the very first problem, which was to do this inside piece first and then find your derivative of that when you're done and prove to yourself that this chain rule part, this part of 2x, is still going to be there. All right, that's not canceled out when we say things like the derivative cancels out the antiderivative, okay, or the integral. So the chain rule part would still be there. So this would be our final answer, which of course you can write this as 2x times the sine of x squared. You're likely to see it like that in a multiple choice question. And by the way, if you're wondering, well, how come we didn't apply the chain rule to our example where the upper bound was x? Well, think about what you're really chaining along. If there's an x, if we chain along its derivative, the derivative of x, of course, is 1, so we don't have to bother to write that. Okay, well, what about a situation if our bounds are reversed? In other words, once again, we're taking the derivative of an integral, but now the constant is up top and the variable part of it is in the bottom. Well, here we just need to use a property of a definite integral, which says, please excuse my barking dog. If we just negate this, then we can flip this around to where we see the variable up top and the constant in the bottom. Okay, so from there, we could simply use our property of canceling these. The negative is still going to be there, so we carry that along. This is going to get dropped in where we see a t in this case. So we're going to have negative e raised to the x cubed, and then we're going to have to chain along the derivative of that x cubed, which is 3x squared. So let's write this as negative 3x squared e to the x cubed. All right, one more. Hence the reason why I wrote one more. So check out how with this problem we have x's in each bound, right? Both the upper and the lower, whereas before we only saw a variable in just one of those parts. So this is a little more complicated, and to help you understand this, off to the side here, recall that we said if we have an integral from a to b, and I'm going to just skip writing the f of x dx part just to save some time and space, okay? But if we have an integral from a to b plus another integral from b to c, we said how there's a property that says that's going to equal the integral from a to c. Right? So from a to b plus b to c, we get the total distance from a to c. Well, if we apply that idea here, if we are starting with, I'm going to just use different color here, if we are starting with 2x, all right, what we're going to do is we're going to introduce a constant, let's call it 0. Okay, doesn't matter what you use, all right, I'm going to just go with 0. All right, so stay with me here for a second. So if we go from 2x to 0 plus from 0 to x squared, would you agree that we would have the same as starting with 2x and ending at x squared? Right? It's the same idea as what we just did up above here. Okay? So what we're going to do in this situation where we have two different variables for our bounds is we are going to introduce a just random constant. All right, I'm just going to usually write it as 0 to keep it simple. Okay, and then we know that that constant is going to disappear when we find the derivative anyway, right, according to that fundamental theorem of calculus. So it really doesn't matter what you throw in there. All right, just shut up and do the problem you're thinking, right? Okay, here we go. So we're really looking to find the derivative of. So we're going to break this apart. We first have from 2x to 0, we have this 1 over 3 plus t dt, plus the integral from 0 2x squared, same thing, 1 over 3 plus t dt. All right. Well, we're going to go one step further with this. If you recall with our last example, we don't want to have the variable on the bottom and the constant up top. So we are going to reverse it. And we can reverse it by negating it. So I'm going to put the 0 down here and the 2x up top. Let's copy down the rest here. All right, this other part is fine. We have the constant on the bottom, the variable on the top. So from there, what we can do is apply the fundamental theorem of calculus, which says that derivative is going to wipe out the antiderivatives. So what are we left with? Well, we have this negative. So we have a negative, and then we're going to have 1 over 3 plus, I'm going to replace this t with 2x, and I have to chain along the derivative of 2x, which is 2. And then same thing over here. This x squared is going to get dropped in right there for t. So I have 1 over 3 plus x squared. And then I'm chaining along the derivative of my x squared, which is 2x. So my final answer here, I'm going to just reverse these terms. So 2x over 3 plus x squared. And then we'd have minus 2 over 3 plus 2x. And that's as far as we will take it. All right.